and Assalamualaikum everyone. We are going to proceed with the qualitative analysis of PN Junction. The meaning of qualitative analysis is the study on the physics of the device, thus no calculation is involved. Calculations will be covered under the quantitative analysis part. Today we are going to focus on the PN Junction band diagram at equilibrium. We have been introduced to PN Junction, which builds up a simple two-terminal device called diode. From now onwards, we will discuss on PN homojunction, which is made of one material, which is silicon, on one side being doped with N-type and another side P-type, as shown in this figure. To discuss further the characteristics of PN junction, the step junction approximations are being applied, which is shown here. In this video, we will discuss on the important concepts of band diagrams for PN junction at equilibrium. Why do we have to learn the band diagrams? The figure shows the current voltage characteristics of a typical diode, which is a PN junction. Understanding a device current voltage characteristics is important for an engineer to design the application of the device, or for troubleshooting, or even to create and invent new devices based on the existing ones. Thus, to understand the characteristics, we must understand the qualitative analysis, or in other words, the physics of the device. For example, what happens in the PN junction that makes a PN junction allows only current to flow in one direction? What makes the leakage current? All of this can be explained and understood by studying the band diagram of PN junction at equilibrium and under forward and reverse bias. In this video, we will first proceed with the band diagram at equilibrium. We start our discussion on the PN junction band diagram with understanding the essential things in the band diagram. Please bear in mind that all PN junction that we are going to discuss in this chapter is a prototype PN junction, of which the assumption is that the device is made with ideal conditions that obeys all theoretical conditions, and on top of that, it is simplified with step junction approximations. So first, let's take a look on the band diagram of N-type silicon and P-type silicon before joining. Both are typical normal homogeneous N-type and P-type band diagram. Recall that the difference between both band diagrams is the position of Fermi level. The Fermi level for N-type is nearer to EC, and the Fermi level for P-type is nearer to EV. I hope you remember the reason why the positions of Fermi level is different for N-type and P-type. Besides the energy levels, other constants that you have to take note are the ionization potential, electron affinity, and most important is work function. The ionization potential is given by EVAC minus EV, and electron affinity is EVAC minus EC. Thus, since N-type and P-type shown here are both silicon, ionization potentials and electron affinities are the same value for both N-type and P-type silicon. But if you have to take note on the work function is given by EVAC minus EV. Since the position of EF for N-type and P-type is different, the work functions for N-type is not the same as work function for P-type. So in short, before joining, both N-type and P-type silicon have the normal homogeneous band diagrams. So what happens upon joining? Upon joining, since N-type has more electrons than P-type, electrons from N-type will diffuse to P-type. Similarly, since P-type has more holes than N-type, thus holes diffuse from P-type to N-type. These carrier diffusions creates the diffusion currents. Remember that electron diffusion current will move the opposite direction of electron diffusion, and holes diffusion current will move in the same direction with holes diffusion. Thus, electron diffusion current will be from P side to N side, the same direction with holes diffusion current. As we have discussed in chapter 4, non-homogeneous semiconductor, the diffusions of carriers will create charge separation. In this case, the electrons at the N side, when they diffuse to P side, they left ionized donors, which are positive ions, and ions will not move, which in turn creates the region as a positively charged area. Holes left ionized acceptors, which are negatively charged at P side, thus this region is a negatively charged region. This charge separation will induce an electric field having directions from N side to P side. Further, the electric field at the junction generates drift currents for electrons and holes, with the same direction with the electric field that is from N side to P side. Besides that, the electric field at the junction will force any carriers that pass through the junction out of the junction region. This will create a region at the junction that has no mobile carriers, which is called the depletion region. So the movement of carriers will continue until the Fermi level is constant throughout the system and the total current is zero. This is the Venn diagram of a PN junction at equilibrium, complete with their respective carrier flux and current directions. You can refer to the tutorial video on how to draw the PN junction Venn diagram at equilibrium. The important concepts that we have to always remember are exactly the same as we have discussed in Chapter 4, especially the consistency of Fermi level. Notice that the Venn diagram has regions of neutral N-type and P-type silicon regions on both sides, of which at these two regions, the characteristics are totally the same as a normal homogeneous semiconductor. A important region that we focus when discussing the PN junction is in the middle, where we have the boundary of the N-type and P-type regions, or the region where the doping changes from N to P. This region is called junction, or transition region, or a few other names which will be discussed later. The formation of electric field at the transition region has been discussed earlier. In short, as the effect from the diffusion of electrons from N side to P side and holes from P side to N side, separation of charge happens, and these two differently charged regions creates electric field across the transition region. Since the separation of charges due to the carrier diffusion creates two regions of oppositely charged ions, the region is known as space charge region and will create the electric field. The electric field across the space charge region has the direction from N side to P side. The electric field will force any carriers that are passing through the space charge region to move out of the region. That means any electrons moving from N to P that is passing through the transition region will be quickly swept out of the region. Same with holes. This will make the region to contain almost no mobile carriers in the region at any given time. We take the assumption that there is no mobile carriers in the region, thus the region is also known as depletion region. So in short, when we talk about the junction, it is at the boundary of N side and P side, which is known as transition region or space charge region or depletion region. When we draw the Venn diagram, since we are obeying the consistency of Fermi level, we can observe a difference in the level of conduction bands and valence bands for N side and P side. This difference is known as the potential barrier or built-in potential or built-in voltage, denoted as VBI. The VBI can be calculated by finding the difference of work function of P side and N side. We will discuss the calculation of VBI when we discuss on the quantitative analysis of PN junction. The next important thing to take note is the junction width. Junction width is the width of the transition region. This width is important because it defines the effective area of the device that influence the device characteristics. The junction width is mainly influenced by the doping concentration. This is because the width simply can be defined by the quantity of charges in the transition region, and this is depending on the doping concentration. If the doping concentration on both sides are the same, the width is the same on both sides. If the doping concentrations are not the same, the junction width is wider at the lighter side of the transition region. For example, in case 1, if we dope one side with Nd equals to 10 to the power of 15 donor and P side having a sector of 10 to the power of 17, the junction width on the P side will be narrower than the junction width on the N side. Case 2 is just the opposite of case 1. The reason behind this is when the doping concentration is high, recombination process has higher tendency to happen. That means more ionized particles will be neutralized and thus the space charge region in the highly doped region will be smaller. This means the area of the transition region is smaller, which in turn means the junction width is smaller. The PN junction that we have discussed extensively just now is made of both non-degenerate N-type and P-type silicon. Depending on the devices, we may have to form what we call a one-sided PN junction. One-sided PN junction is a junction having a degenerate semiconductor on one side and another side a non-degenerate semiconductor. The degenerate side is denoted with the plus sign. For example, a N plus P junction is a junction having degenerate N-type and non-degenerate P-type. The important thing that we have to understand here is when drawing the Venn diagram, the side having degenerate material will have overlapping energy levels. For a N plus P, at the degenerated N side, EC will be overlapping with EF. For P plus N, at the degenerate P side, EV will be overlapping with EF. And since one side is extremely highly doped, the junction width is taken mostly on the non-degenerated side. That's the end of Venn diagram under equilibrium. To summarize, the movement of carriers and currents in the junction obeys the theory of diffusion, formation of electric field, and also drift current. All the important things such as formation of electric field and built-in voltage, which are happening in the PN junction, are at the boundary of the N side and P side, which is also known as transition region or space charge region or depletion region. The width of this region is called junction width, which is larger at the side having lighter doping. And finally, there is also a type of PN junction, which is one-sided PN junction. This PN junction has a degenerate material on one side and a non-degenerate material on the other side. So that's all. I hope you understand the Venn diagram at equilibrium and be prepared to understand the Venn diagram under bias. If you have any question, don't hesitate to ask. Thank you.